So let us now test the backpropagation part before we use our optimizer for running it automatically. So therefore, let's go to our test script. And of course, we want to import our LSTM. And we want to use just or start with a very moderate number of neurons. So we just want to test it. And then, of course, we also need the length of the data set. And then we have to call our dense layers, which turn the output from the LSTM, so H, so the list containing all the state vectors H, into the predictions Y hat. So we also need to call those dense layers, and I'm going to say a few words about those dense layers. But they're responsible for turning HT, so the output from the LSTM, into Y hat, the actual prediction. And then we also want to start off with a relatively moderate learning rate, and also with a relatively small number of epochs, because we just want to see the progress. And we want to monitor the loss for every epoch, and that's why we want to set up such a vector called monitor. Yeah, and then we start just with the loop where we call the forward part, and then the forward part generates H, the vector containing all, or the matrix containing all the state vectors. We also need to reshape it a bit, and I show you why. And of course, when we start our LSTM in the forward part recursively, then we have to start with the initial values in H. But then they are used for calculating the actual output H. So therefore, we have always one more set of values H, and those at the beginning, so these are just the vectors always only containing zeros, are not needed for calculating the actual prediction Y hat. So we just remove the first entry, and also want to show this in more detail when we have the code, what it actually means. So we want to remove the first entry and then take this, feed it into the forward part of the dense layer, and then it creates or calculates Y hat that we compare to our training data. And that gives us the first order derivative, dy, and then we take it in and put it back into the backward part. And then also those dense layers have already a backward part, and I will show you this. And the output from the last dense layer, so the inputs are the values for the backward part of the LSTM, and then it calculates all the changes of the learnables that we have calculated in the last session. And then we change the learnables accordingly, and not only those from the LSTM, of course, also those from the dense layer where we have different weights and also the biases. And then we have to do this for all the learnables of the LSTM as well. And also we want to print the current loss, and also want to create a plot of how the loss changes over the different epochs. And hopefully we're going to see something like that, so that the loss really drops smoothly over the number of epochs, so there are no oscillations. And also when we print it out, we of course start with a relatively large value because we start with random numbers, but then running through the different epochs should actually really show us a clear improvement of the loss. So that's the idea. And now we want to implement this into our code. So therefore, let me just change the screen and let's go to our code. And it also makes sense now, again, to set up a new folder. So we just create a new folder according to the chapter. So let's call it 3 full backpropagation. And then, of course, we want to navigate to this folder. So we just go to the current folder, and then also want to save our current work in the new folder. That was a warning. Okay, so here we go. All right. So now let's first of all call our LSTM. So let me just compile it, and let me just call the LSTM, and let me also just create the forward part. So we have our LSTM, we have a certain number of neurons, and then we just run this part, and then we just run the forward part. So we just have now the forward part and feed xt into the forward part. So what happens based on xt, it creates, for example, h. And let's take a look at h. So h is our list. And for every time point, it contains the state vector. And it has as many state vectors as states we have given by implementing or calling the LSTM, so the number of neurons. So this is our number of states. So it has 200 of those entries each. And that's what you see here. But of course, it has more entries or more of those vectors than time points. It's just one more. So because t is the number of time points, it's 800. But we have to start with an initial set of values for calculating all those values in the first LSTM cell in the first place. So the first prediction, so the prediction I had for the first time point actually comes from the second entry of age. So that's the reason why we have one more value, because we need an initial value, so to say. And we have to translate or turn this into our prediction y hat. And we're going to do this with the dense layer. So let me just first of all show the dense layer. So I copied and paste already the dense layer. And so this is the dense layer we created during the other lectures, A and N for Scratch and C and N for Scratch. And if you haven't watched that, you can just go to the GitHub repository and copy and paste that. What is important is that we have, of course, an init, and we have a forward part, and then we have a backward part, which takes care of all those derivatives. So you get the d values, that's the input dy, and then put it into the backward part, and then it multiplies the values with all the inner derivatives and calculates the change of the weights and the biases, and also the inputs, which is for the next layer if you have a sequence of dense layers. Also important is to understand what is n inputs and what is n neurons. So, of course, so n inputs is the number of features we have for every data point. So when you, for example, have a data point with 3 dimensions or so, n inputs is 3. And the number of neurons is a free number, so you can just choose as many neurons as you like in principle, and it will all just work out. But n inputs here refers to the number of features for every data point. And if we want to now set up the first dense layer, and we just call layer dense, that I have copied and pasted already in our LSTM. So let me just show this again so that you can see the structure. So then it asks for the number of inputs and for the number of neurons. So the number of neurons here has nothing to do with the number of neurons here. It has to do with the number of inputs. And I also want to show this. So for example, let us first of all go to H, because H is the vector of states, and we want to translate it using the dense layer into the predictions y hat. So H has to be turned into y hat through the different layers. And let us take a look at H itself. So first of all, we want to turn it into an array. So we just say np array. And we just, we have our H already. So this is an array. Our list now is an array, 801 times 200 times 1. So why is it 801 again? Because we have 800 time steps, but we have to start with an initial value before we feed it into the LSTM cell in the first place. And we have 200 states because that's the number of neurons here. So, and it also has a third dimension, so we actually don't need that. So let me just reshape it. So then we just say reshape. And we just do this according to the shape of H. So we have H shape. The first entry, that's the number of rows. And the second entry, it's the number of columns. And this is our new H, let's call it like this. So now we have a flat matrix, so to say, just two-dimensional object. So again, this is the first row are the initial values when we set up H in the first place. I also want to show this again. So when we just set up H in the first place, then of course we need the initial values for feeding so putting into our LSTM cell, and then generate the first value y hat based on this. So we have our matrix H, and then we put it through the forward part, and then for every time step it calculates H, and this is the value we have to translate into y hat. So this is like, so for every time point, we have 200 values. So therefore, every time point has 200 features. So every row stands for a time point. So this is the initial value. Then we put it into the cell. It calculates H for the first time point. And here it is. And then for the second time point, and so on. So for every time point, we have as many columns as number of neurons. So the number of features actually is the number of neurons here. And this number is the number of neurons in the dense layer. So we also want to set up a second dense layer, which then finally converts the input into the prediction y hat. So this is the number of features, which is now the number of neurons we have here. We don't know what this number is, but we also know this number here has to be the same as this number here. So that's what we discuss in the lecture ANN from scratch. In principle, you can just think about it that if you just call two dense layers subsequently, and just hand over the output, so you create an input here, and then you create an output and use it as an input for the next layer, then this number has to be the same as this number, otherwise the shapes don't add up. So this number, so the number of neurons here in the first dense layer equals the number of features in the second dense layer. And this number is completely free. So how many neurons should we implement? Well, we have t time points. Why not, for example, just saying t? So this number is t. So then the question is, what is this number? So we want to turn H into y hat. So for every entry here, so this is for every time point we have this vector. And at the end, this should be just one single number. So for every time point, so for every row, we actually only need a single number because that's the prediction y hat. So therefore, this is 1. Because for every time point, we just need one value. That's the prediction y hat. For example, when we created the CNN from scratch, we had different categories where we had these different images, and then every output neuron was voting for one particular category, and this was the number of categories. For example, when we had different digits, 0, 1, 2, 3, up to 9, then we had 10 different categories. So this was 10, but in our case now we just have one single value. So we have only one output neuron for every time point. So it's also a classical regression problem. So because we just want to fit this curve in a sense, so this is just a regression problem, so we just have a number each. If you have a classification problem, then after the last dense layer, you have to turn it into probabilities, and you can do this with a softmax layer. So the only difference then is adding a softmax layer in the same way we also did in the previous lectures, where we created a softmax layer and used the softmax for categorizing the different images. Also here, if you don't know the details, it's not important for this particular lecture now, but if you're interested, please take a look at the other lectures. But I just want to mention that there's of course the possibility to turn this, if we have a regression problem, to use an additional layer, which is the softmax layer in the case, if we have a classification problem. Okay, so now so now we called all these layers. So let me just call this again here. And again, if you want to do that, please first of all copy and paste the dense layer from the GitHub repository. And now we can set up our backpropagation. So first of all, we want to start with a relatively small learning rate. And we also want to start with a certain number of epochs. So let's say an epoch is 100. So a relatively moderate number. And now we want to just run, or let me just first of all create monitor, so the matrix that monitors the loss, which has the length 100. So now, now let's run our loop. So for n in range n epoch, we first of all need to call the forward part. So we just say LSTM forward xt. Then this creates h as an output. So this is what we have here, but we need to turn it into an array. So we can actually copy and paste this part. So we just create, no, we want to copy paste this part. So we just create an array from h. So it calculates then h for every time point. And you also have seen that we need to reshape h. And now we have this structure here. And now we want to turn this structure or feed it into our dense layer. So just really see it as 800 data points, and every data point has 200 dimensions in our case. So we then call the dense layer, the forward part, and then we have to put or have to take age as an input. So you saw that the first row are just the initial values. So they have nothing to do with the prediction y hat, whereas those values have to be translated into y hat. So we actually don't need the first part, and we just remove it. And we can just do it by saying I have age, the first slice, then everything else that comes after it, and all columns, of course. Let's call it age test because I also want to show you what it looks like. So we have now all those values, except the initial values, because we just needed the initial values for running the LSTM cell in the first place. So we now have 800 values. So we just take all values but the first row and feed it into the dense layer. And then we take the second dense layer and take the output from the first dense layer. So here we go. And that creates an output, which is the prediction y hat. So that's a translation of the states into an actual output. So we did quite a lot now. So let me just test it. So of course we want to, let me just rerun this and let me just test whether we get an error message or not. So we run the forward part. Then we create age. And then we take age and put it into the forward part of the first dense layer. And this generates an output, which we use as input for the forward part in the second dense layer. And that should create y hat, which is a vector of length 800. So let's also test this. So it has the length 800. So also just to show you that again, so we started with age. Then we removed the initial values because we needed them for running the LSTM cell in the first place. So we have one data point. So every time point is one data point with 200 dimensions, and we have to translate it into one single data point. So now we have y hat. And now we can calculate the loss. And we also want to calculate the loss itself. So this is just the difference between the prediction and the actual data, dy, and dy is the outermost derivative if you want. So then we also just want to calculate L because we want to plot it and want to see how the loss changes over time. So we just have used the dot product of dy with itself, which is element-wise multiplication and then summing it up. So we have something like the sum of the squared errors and divided by t gives you something like the mean. And then we want to save it, of course, in monitor n equals L. And this is the forward part. So this is the forward part here. Let's, for example, calculate L. We just have random numbers, so nothing has been optimized yet. This is just an arbitrary number, but they have an impression of L, so like 2 point something. So this is the forward part, and now we just start with the backward part. So this is the feedback from the loss function, and this is the outermost derivative. And now we have to put it into the backward part of the dense second dense layer. So these are the d values, and then it multiplies the outer derivative, all the inner derivatives for calculating the change of the weights and the biases, and also calculating the inputs for the next adjacent layer. So we just then used called dense to backward method, and the d values is just dy. And then we call this first dense layer the backward method, then gives me just the output, so the d values from dense 2. Which are called the inputs. Just to show you where it comes from. So these are the inputs here. So then that generates also the D inputs from the first dense layer. And that's the feedback we need for the LSTM. So, and now this is the feedback that it's used here. And also here. And now it just triggers all those calculations here, and hopefully in a correct way. And then we have to change the different values for the learnables, which is, of course, a bit more technical part. So we just change the learnables for the different layers. So for the dense layer number 1, then dense layer number 2, and we do this for the biases and for the weights with the corresponding learning rates. And we also have to do this for all the other learnables. And also here, this is just a very technical part. So just copy and paste it here. So we do this for the vectors U for the different gates. We do this for the matrices W for the different gates, and of course for all the different biases. And you see there are lots of learnables. So that's a relatively complex network already. And we use the same learning rate for all the changes here. But we actually don't have to. And that's actually one thing you could do if you want to optimize the training process. You don't have to have the same learning rate for all the different learnables. There's actually, you can actually have a learning rate vector, and you can also have an individual learning rate decay or learning schedule for the different learnables. So they don't have to be the same values necessarily. In fact, it actually optimizes the process if they're not the same. So because maybe some learnables may change faster or slower, that really depends on the system. So that we have the same learning rate here is just convenience. It doesn't have to be. And in fact, it's actually, as I said, it actually would improve the learning performance if they're not the same, if they're really adapted to the different learnables. But we just want to keep it simple and want to leave it as it is. So now we also want to print, of course, the loss. Maybe we can just say, we use fstring and just say current MSSE equals, and then we just have the value. So we want to just print L, and yeah, like 3 digits, I would say. Okay. And then we also want to create a plot. And this is also just the technical part. So after the loop, we want to create a plot of all the results. So we just have the range of the number of epochs. Which is the x-axis. Then we have x label and y label. And we probably also want to change the scale a bit. So we just say plot y scale is then just log. Because you probably might come from pretty large value, even though if L is pretty moderate, but just that we cover the entire dynamic range. So let me just show this again. So what did we change? So first of all, we added the dense layer. Again, this is just copy and pasting from the codes we have already from the previous lectures. If you haven't watched them, just copy and paste it from the GitHub repository. And the dense layer automatically takes care about the derivative, so it has a backward method already. So we can just use it directly. And the dense layer translates H into Y hat. How does the dense layer work? So you have the number of inputs in the first dense layer, then you have a number of neurons which are free. Here the number of inputs is the number of features, which is the number of neurons we gave, because that gives us the size of the state vector. But in general, this is the number of features. But again, I want to show you that. So we have 200 features here for every time point t. Then this variable is the number of neurons in the actual layer, which is free. Let's say it's t because we have t time points. So that's definitely not under and overfitting. And then we need the number of neurons for the output. And we just have one because we just want to have one value for every time point. This is a classical regression problem because this value has to fit a prediction. If you have a classification problem, then after the dense layer, there should be a softmax layer as well. Then the forward part is complete, and then we have the backward part here. So let me therefore just run let's run this again, even though I just called it already. So let me just run the forward part just completely again. And then let's check the backward part, whether we get an error message or not. So this seems to work. Then we have the inputs, and then we also would change the weights here. So this seems to work. And now we are actually ready for testing it. So we want to create a plot here. And let me just remove the plot. So we can just, so let me once more again run the LSTM and compile it. And now let's run this. And let's see whether it goes down. And actually that looks pretty good. So the values go down. It is not perfect yet, so we can still change a bit the learnables, like the learning rate or the learning rate schedule. There's no momentum, there's no decay, but it actually looks pretty good. So it just goes down with every step. There's no oscillation, and the fit seems to work. But let me just finish that. And then let's take a look at the plot. And you should kind of see the same behavior. So again, it's not perfect because there's no momentum, there's no learning rate schedule. The learning rate is the same for every learnable, so there's lots of space or many options where we can optimize it. So, and it's also again relatively slow because my computer is running Zoom in the background and the two monitors, but it should be pretty fast actually. But let me still finish that, and here it is. And it's a very smooth curve. And that's a good sign. So the backpropagation part works, and therefore we can perform the next step. And the next step is then using an actual optimizer and modifying the optimizer. So our backpropagation part works, and now we want to modify an optimizer that we have already. So that will be the standard stochastic gradient descent optimizer. And also that's an optimizer we have been using in all the other lectures. So we're just gonna modify it. And again, also here, if you haven't watched the other lectures, just go to my GitHub repository and copy and paste the optimizer, and then it will work immediately. So then let's explore the optimizer in the next chapter.